By this point in the series, you may know a lot of different necessary and sufficient conditions for a matrix being invertible. For example, one condition that you may know is that A is invertible if and only if the reduced row echelon form of A exactly gets us the n by n identity matrix. And of course, it's implicit that A is in fact an n by n matrix. For us to have an isomorphism between the vector spaces, the dimension of the domain and codomain certainly has to be the same. We can also say A is invertible if and only if the determinant of A is non-zero. This is one that we touched upon in the previous episode. And yet another equivalent condition that you may know if you've been doing the problems is that there exists an n by n matrix B such that B times A is the identity matrix. And the reason this is true is that rank of A has to be n here, because if rank of A is strictly less than n, then B is getting inputted something of dimension less than n, so B is going to output something of dimension less than n, and we certainly cannot have this equality with identity matrix here. So we know rank of A is n, and A is in fact invertible. And here I encourage you to pause the video and list a few more items here. There are certainly many more. But for now, we will move on and address a very natural question of how do you actually compute A inverse when A is invertible? So the question is, how do we find A inverse? Well, one way of doing this is to start with A and realize that if A is invertible, so we can multiply elementary row matrices to the left, so M1 all the way to some M sub n, and get the identity matrix. So recall that these are elementary matrices that we introduced in the previous episode. Then it follows that if we multiply A inverse here to the right, A and A inverse cancel out to get us the identity matrix. So we in fact get that M sub n all the way to M sub 1 times the identity matrix is equal to A inverse. And what this is telling us is that if we row reduce A, so we may be scaling a row by a factor of 2, we may be adding a multiple of one row to another, and here we're doing exactly the same row operations now to the identity matrix, and we're getting A inverse. So that's telling us that we can find A inverse by row reducing A, and whenever we apply an elementary row operation, we are going to apply the same row operation to the identity matrix, and we are going to get A inverse. Okay, so hopefully that was a nice summary of matrix invertibility. Now let us go on to a topic that we are going to study for this episode and the next two episodes, the one of matrix similarity. Let's say we have a linear operator phi on R2, and let's say phi is sending E1 to say E1 minus E2, and let's say it's sending E2 to 2E1 plus E2. And by now, you should immediately see that this exactly corresponds to the 2x2 matrix, where we're writing the matrix with respect to the standard basis E1, E2, and namely that E1 is going to be sent to 1 times E1 minus 1 times E2. So we're going to have 1 minus 1 here, and E2 is being sent to 2 times E1 plus 1 times E2. So we know this is one way of writing this matrix. But now, let's try changing the basis. Let's say I give you V1 and V2, where V1 is 5E1 plus 2E2, say, and V2 is 3E1 plus E2. I leave it up to you to think about why V1 and V2 are linearly independent and in fact a basis of R2. But something you can realize is that the same phi, so exactly same linear transformation phi here, is going to send a V1 to negative 18 V1 plus 33 V2, and it's going to send a V2 to minus 11 V1 plus 20 V2. This is something you can just check explicitly if you really want to. For example, since we know where E1 and E2 are being sent to, we can explicitly find where V1 is being sent to in terms of E1, E2, and you can now convert that back to in terms of V1, V2, in the span of V1, V2, and you'll find that that's minus 18 V1 plus 33 V2, and similarly for V2. But the main point here is that we can also write phi as the matrix negative 1833 and negative 1120 if we're now writing it with respect to V1, V2. So V1 is being sent to minus 18 V1 plus 33 V2 and so on. So let's call this matrix B. And here obviously A and B are very intimately related. Both of them arise from the same phi. And in such a case, we say that A and B are similar matrices. So I wrote down the matrices A and B here. A natural question that you may ask here is whether there are any nice ways of converting between A and B, converting between the bases. And a pretty elegant way that does the trick is to use what's called a change of basis matrix. Namely, we're going to go from V1, V2 to E1, E2 to cancel out E1, E2 intermediaries here. And then we are going to go convert from E1, E2 to V1, V2 to cancel out E1 and E2s here. We know V1 is 5E1 plus 2E2. So let me just write down 5E1, 2E2 here. And we know we can go from V2 to E1, E2 by writing V2 as 3 times E1 plus 1 times E2. And if we want to go backwards, so if we want to go from E1, E2 to V1, V2, then that's simply going to be 5, 2, 3, 1. And we're just going to take inverse of this matrix. To summarize, what we have really shown is that A and B being similar is exactly equivalent to having some invertible matrix S, such that B is equal to S inverse times A times S. And this entire operation is usually called change of basis, as we may expect. For this particular example, certainly it doesn't really matter if we use E1, E2 or V1, V2, but there are cases where it is probably going to matter quite a bit which basis we are going to choose. Just to give you an example, let's say we have a rotation in R3, so this is the z-axis, x-axis, and the y-axis, and let's say we have some x's here, and let's say we're rotating any point in R3 by data degrees counterclockwise about this axis. So for example, if you consider a plane that's orthogonal or perpendicular to this axis, then any vector on this plane is being rotated by data degrees to another vector on this plane. You can show that this map is linear as long as the axis is going through the origin. And something to realize here is that if you have to write this map in terms of E1, E2, E3, well, that's going to be a nightmare, right? But writing this map with respect to some other basis is going to be much easier. For example, we can pick V1 and V2 that are parallel to this particular plane here, such that V1 and V2 are perpendicular. So let's say we have V1 like this, and V2 has the same magnitude, same length, and let's say we have 90-degree angle between these two. And let's say we very naturally pick V3 to lie along this axis. And now, with respect to V1, V2, V3, we have a much easier time writing this linear transformation. So we can work with data, but just to make it a little easier, let me work with data equals to 90 degrees. When we apply this rotation, V1 is going to rotate to V2. So we're going to get V1 being 0, 1, 0. V1 is being sent to V2. Whereas V2 is going to rotate 90 degrees to minus V1. So we're going to have minus 1, 0, 0. And finally, V3, when we rotate it, is going to stay the same. So V3 is going to be 0, 0, 1. It's going to be sent to itself. And this matrix is certainly way nicer than the matrix would look like if we have to write it with respect to E1, E2, E3. Okay, now let us transition to thinking about how similar matrices are. If A and B are going to be n by n similar matrices, what kind of properties are they going to have in common? And I guess we'll specify here that A and B are n by n real matrices, so we are working over Rn here. Certainly you can also consider the similarity for vector spaces over any field F, not just the real numbers, but we'll just focus on the real numbers here. To start off, realize that if A and B are similar, then rank of A is going to equal to rank of B. To see why this is the case, realize that B is equal to S inverse AS for some invertible matrix S. So if you consider what the image of B is going to be, certainly the image of S, because S is invertible, is going to be the entire space Rn. And then we're plugging Rn into A, which is going to output a space of dimension rank A. And then, because S inverse is invertible, as you can check, if we are inputting a dimension of rank A here, then we're going to output space of dimension rank A. So the rank of B is in fact going to equal rank of A. Yet another property that we can check is that determinant of A and determinant of B are going to be exactly the same, for the simple reason that if you just calculate the determinant of B, as we saw in the previous episode, we can split up the determinant of S inverse AS as determinant S inverse, determinant A times determinant of S. And something to realize here is that determinant of S inverse times the determinant of S is going to be determinant of S inverse times S, which is the identity matrix. So that's going to become 1, and they're going to cancel out. So we exactly get that determinant of A is equal to determinant of B. And I guess another thing I can add here is that trace of A is equal to trace of B, where trace of A is just defined to be the sum of the diagonal entries. So for example, trace of A, B, C, D we are just going to add up the entries in the diagonal. So trace of A, B, C, D is just going to be A plus D. To see why this is true, one way of seeing this is to just show that trace of, say, any A times B, where A and B are n by n matrices, is going to equal to trace of B times A. And this property is something I encourage you to show if you're interested. The proof just consists of multiplying A times B, multiplying B times A. Just brute force multiplication. You can just add up the diagonal entries and you'll see that the sum of the diagonal entries are going to be the same, even though the diagonal entries themselves are not necessarily going to match. Since this is very tangential to the theory of similar matrices, I'll just take this for granted. And something to realize here is that trace of B, let's say S inverse AS, is going to be equal to, using this property, trace of AS times S inverse. So here I'm simply grouping this as S inverse times AS, and I'm simply switching the two. And then this is, of course, a trace of A. So we have established this. I can continue down this list. For example, we can say that A squared and B squared are going to be similar matrices. And this is simply because when we try to find B squared, this thing is going to be S inverse AS times S inverse AS. And we see that we can simply cancel out S and S inverse here to get B squared being S inverse A squared S. So that's telling us that B squared and A squared are similar once again. And of course, this argument can be extended to show that A to any L power and B to any L power are similar. So I guess up here, we can also say rank of A to the L is equal to rank of B to the L as one of the consequences of A and B being similar. But let me just add one more to the list. And for this, I want to just introduce the notion of a nilpotent matrix. And a nilpotent matrix is the one that for any vector V, if we apply A to V enough times, so let's say we apply A to V once, and then maybe we apply A to AV again, and then so on, so we are applying a bunch of times, then we are going to get a zero vector. So we can make any vector in Rn vanish by just applying the matrix enough times. And a fascinating fact that I'm not going to prove here, this is something you can try to prove right now if you really want to, but we'll probably see a proof of this in a future episode. And the statement is that if A is nilpotent, then A to the nth power, where n is the dimension of the vector space, is equal to the zero matrix. And this is certainly a fascinating fact, but let us just take this for granted for now, and let me state that if A is nilpotent and A and B happen to be similar, then of course B is also nilpotent. And proof of this just requires you to realize that B to the nth power, once again, is going to be S inverse A to the nth power S. And since A to the nth power is a zero matrix, everything is going to disappear. So B is nilpotent as well. Okay, all of these properties of similar matrices are pretty nice to know, but a natural question remains. Is the converse true? Like, for example, let's say I give you two matrices A and B, such that rank of A is equal to rank of B. Those that imply A and B are similar. If I give you two matrices whose determinant is the same, then those that imply that A and B are similar. Can we go backwards in this paradigm? And the answer to all five of these properties is no, you cannot go backwards. Let me try to convince you of that. For example, let's say you have rank of A is equal to rank of B. Let me give you A and B that are not similar. So let's say A is the identity matrix 1, 0, 0, 1, and consider B to be, say, 1, 0, 0, 2. And now you should see that A and B are not similar because determinant of A is 1, whereas determinant of B is 2. So these are not similar matrices. And of course, this is despite the fact that rank of A is equal to rank of B, both of them have rank of 2. Now, what about determinant of A being equal to determinant of B? Does that imply that A and B are similar? Once again, the answer is no. I guess you can work with the same identity matrix if you want to. And let me now use 1/2 0, 0, 2. And the reason that A and B are not similar is because if they were, such that B is equal to S inverse times A, which is the identity matrix, times S, then of course this is going to force B to be the identity matrix as well. But B is not the identity matrix, so A and B are not similar. And we can certainly continue this. I mean, trace of A equals to trace of B, you can similarly disprove using 0, 1, 0, 0, 1, and I guess you can use, for example, 2, 0, 0, 0. And the reason A and B are not similar now is because A has rank 2, but B has rank 1. Now we come to a tricky one. Can we find a and b such that a squared and b squared are similar, but a and b are not? And we certainly can. And just to make this a little more interesting, let me use a to the fourth power and b to the fourth power, and leave the case for a squared and b squared up to you. It shouldn't be too hard. And for the fourth power, let me suggest a being 0, 1, 1, 0, 0, 1 once again, and b equal to the rotation by 90 degrees in R2. So such a matrix, if you remember our reasoning earlier, is going to be given by, with respect to E1, E2, 0, 1, and negative 1, 0. And of course, because B is rotation by 90 degrees counterclockwise, B to the fourth power is going to be the identity matrix. And here, of course, A to the fourth is also identity matrix. So we see that A to the fourth and B to the fourth are similar, but A and B are not. But in fact, I claim something much stronger. I claim that B is not similar to any diagonal matrix. So a diagonal matrix is a matrix that have some diagonal entries, A, B, C, but all entries other than the diagonal entries are going to be zeros. So I guess for the 2 by 2 case that we have here, we are just going to have A, 0, 0, B. And I claim that B is not similar to any diagonal matrix, which is another way of saying this is that B is not diagonalizable. So the term diagonalizable simply means that you are similar to a diagonal matrix. And to see why B is not diagonalizable, realize that here B is being written with respect to the standard E1, E2. And let's say, just suppose for the sake of contradiction, that B happen to be diagonalizable such that we have some V1, V2 with respect to which we have this matrix. But if that's the case, realize that here the linear transformation phi is sending V1 to A times V1, so we're just scaling V1, and V2 is being sent to also B times V2, so V2 is being scaled. And if a non-zero vector like this is simply getting scaled under the transformation, we say that these vectors are eigenvectors. And we're going to talk about eigenvectors much more in the next episode. But the point of the matter here is that if B happen to be diagonalizable, then B should have eigenvectors. But think about this. B is a rotation by 90 degrees counterclockwise. How can you have an eigenvector? How can you have a vector that you're just scaling? Of course, you do not. So B cannot be diagonalizable. And just to finish up, let me consider the converse of 5. I guess it's kind of unclear what the converse should be, but let me show that if A and B are nilpotent matrices, then A and B do not have to be similar. And let me show you a pretty nice example. I guess you can consider a matrix like 0, 1, 0, 0, 0, 1, 0, 0, 0 as A. And let's say we consider B to be a matrix given by 0, 1, 0, 0, 0, 0, 0, 1, 0. And something you can check is that A and B are nilpotent. You just have to show that A cubed is equal to B cubed is equal to 0. But of course, A and B are not similar because rank of A is 2, but rank of B is 1. Okay, I hope this was illuminating. And we're going to continue talking about nilpotence, diagonalizability, and so on in the next 2 episodes, which are going to be the final 2 episodes of the series. So thank you for watching, and I hope to see you in the next episode.